November 1942, Pacific Theater, Central Solomon Islands. American naval bombers were dropping from the sky at a rate the military brass hadn't anticipated. The dauntless dive bombers, the Avengers, the Wildcats, all of them were suffering catastrophic structural failures not under enemy fire, but under the very conditions they were designed to endure. The fuselage was folding. The wings were tearing. The tail sections were snapping off during high-speed maneuvers. The problem wasn't enemy accuracy. The problem was aluminum. Since the late 1930s, American aeronautical engineering had standardized on aluminum alloys, specifically the 24S variant, an aluminum-copper composite that offered a decent strength-to-weight ratio. It was relatively cheap, it could be machined quickly, and it satisfied the urgent production demands of the pre-war military expansion. But aluminum has a critical vulnerability. It fails catastrophically under repeated stress cycles. It doesn't bend gracefully. It fractures, and in a dive-bombing run, where a pilot pulls up to 7 Gs in a matter of seconds, the fuselage experiences stresses that 24S aluminum simply cannot withstand indefinitely. The data was brutal. Between 1941 and 1943, the U.S. Navy logged 884 aircraft lost to structural failure in the Pacific Theater alone. That's not combat losses. That's training accidents, mid-flight disintegrations, and catastrophic failures during combat maneuvers. Across the U.S. Army Air Forces, the number was worse. Over 2,000 to 300 documented structural failures. Each aircraft that vanished cost approximately $40,000 to $60,000 in 1942 dollars, the equivalent of nearly $800,000 in modern currency. More critically, each loss represented a trained pilot, a navigator, and often a full crew of 5 to 10 men. The crisis wasn't hypothetical. In October 1942, during the Battle of the Coral Sea, a squadron of 18 dauntless bombers was dispatched to strike a Japanese cruiser group. 14 made it to target, 8 returned. The remaining 6 didn't suffer from anti-aircraft fire. Gun cameras and Japanese records confirmed that. 3 of them experienced catastrophic wing failures during high-G pullouts. 2 disintegrated mid-air for reasons the recovery teams could only classify as structural anomaly. One pilot reported in his final radio transmission that his controls had become unresponsive and his wing was flapping. Those weren't metaphors. They were technical descriptions of metal reaching its breaking point. By December 1942, U.S. Naval Aviation Command had escalated the problem from an engineering concern to a strategic threat. Fighter pilots, who were already suffering 40% casualty rates in engagements with Japanese Zero fighters, were now additionally risking death from their own aircraft. Combat readiness was being constrained not by enemy capability, but by mechanical reliability. Air group commanders were being forced to issue standing orders. Do not exceed 6 Gs in any maneuver, and do not perform extended combat roles at speeds above 320 miles per hour. These restrictions were crippling. They meant that American pilots, flying superior numbers, were deliberately handicapping their own performance to prevent their planes from disintegrating. The strategic calculus was unforgiving. The Japanese were producing approximately 450 aircraft per month by late 1942. The United States was producing 1-200, but if 12% of them were being lost to structural failure before they even reached combat zones, the numerical advantage dissolved. At current attrition rates, the U.S. would need to produce over 1,800 aircraft per month just to maintain operational strength in the Pacific. The industrial capacity existed, but the aluminum supply chain was already stretched to its absolute limit. By January 1943, the crisis had reached the highest levels of the War Department. General Henry Hap Arnold, commanding the Army Air Forces, issued a classified memo to the chief aeronautical engineer at Wright Field, Ohio. Find a solution within 6 months, or the entire strategic bombing campaign in the Pacific would be suspended pending design review. That wasn't a threat. That was a prediction of operational collapse. The material wasn't strong enough. The design couldn't be modified further without adding weight that would negate the speed advantage of the aircraft. And the production timeline was non-negotiable. There was a war being fought. The requirement was impossible in the language of classical materials science. Develop a metal alloy that could be produced at scale, that could be machined with existing industrial equipment, that could be riveted and welded using wartime methodologies, that would be approximately 20% stronger than existing 24S aluminum while weighing no more, and that could be implemented into the existing production pipeline within 5 months. By conventional engineering standards, it couldn't be done. But between 1935 and 1942, a line of research had been quietly developing in university laboratories and industrial metallurgy divisions across the country. It wasn't being funded with military dollars. It wasn't classified. It was the work of pure material science, the systematic testing of zinc, magnesium, and copper additives to aluminum in varying ratios, searching for the combination that would produce superior strength without brittle failure modes. That research had produced a candidate, 7075 T6 aluminum. In January 1943, that candidate moved from the laboratory to the engine of industrial warfare. The problem landed on the desk of Enner Hertzberg in late January 1943. Hertzberg was the chief metallurgist at Alcoa's research center in New Kensington, Pennsylvania, a 45-year-old German-born scientist who had spent the previous 8 years systematizing aluminum alloy research into a reproducible science rather than industrial trial and error. His team consisted of 4 senior materials engineers, 2 technicians, and access to Alcoa's precipitation hardening laboratory, a facility that had been developing advanced alloys since 1935, but had never been asked to solve a crisis this immediate. The directive was categorical. Validate a production-scale aluminum alloy capable of 70,000 pounds per square inch tensile strength, nearly 40% higher than existing 24S, without exceeding the weight specifications of existing airframe designs. The alloy had to be machinable, weldable, and rivetable using 1943 industrial methodologies, and it had to be ready for full-scale production by June 1943. Hertzberg's team didn't invent 775 T6. That would be a misreading of the historical record. What they did was accelerate a metallurgical principle that had been documented since 1935. Zinc, copper, magnesium additives in aluminum produced superior strength through a specific heat treatment process called precipitation hardening. The theoretical work existed. The laboratory data existed. What didn't exist was proof that this alloy could be manufactured at scale without catastrophic variability in batch quality. By February 3, 1943, Hertzberg had redirected Alcoa's entire experimental capacity toward refining what would become known as 7075 T6. The T6 designation wasn't arbitrary. It specified the exact heat treatment sequence: solution heat treating at 900 degrees Fahrenheit, water quenching, aging at 250 degrees Fahrenheit for 24 hours. The precision was mandatory. Deviation from any of those parameters by as little as 15 degrees would produce an alloy with either insufficient strength or excessive brittleness. The first production-scale ingots were cast on February 15th. They failed. The ingots showed internal segregation. Zinc and copper compounds were concentrating unevenly throughout the material rather than distributing uniformly. Under stress testing, they fractured in ways that were predictable but unusable. The team regrouped. Hertzberg issued a memo. The problem wasn't the alloy composition. It was the ingot casting temperature and cooling rate. That margin of error had to be narrowed from plus or minus 50 degrees to plus or minus 8 degrees during the casting process. Alcoa's casting supervisors said it was impossible. Industrial-scale furnaces in 1943 didn't have thermometric precision at that level. Hertzberg's response was direct: develop it or lose the contract. By March 1st, Alcoa's foundry division had implemented a system of external thermocouples and manual cooling rate adjustments that achieved the required tolerance. The first batch of compliant ingots was ready for heat treatment on March 8th. The second failure came during the aging phase. At 18 hours into the 24-hour aging cycle, one experimental batch showed stress corrosion cracking, tiny fissures propagating through the material under static tensile load. This wasn't a production defect. This was a fundamental material science problem. The alloy was chemically reactive in ways that previous formulations weren't. Zinc and copper under specific conditions created a galvanic cell that accelerated corrosion along grain boundaries. The solution required adding 0.08% chromium to the alloy composition. Chromium is a grain boundary stabilizer. It doesn't improve strength. It prevents the chemical environment inside the material from degrading the crystalline structure. The modification was approved on March 19th. New ingots were cast with chromium addition, tested at 24 hours into aging, and produced tensile strengths of 73,000 pounds per square inch with zero cracking propagation. But there was another problem: machinability. The 7075 T6 was significantly harder than 24S aluminum. Existing machine tools, the drills, lathes, and cutters used in aircraft manufacturing, were running at speeds that were generating excessive heat and tool wear. A drill bit that could machine 100 holes in 24S aluminum could now only machine 12 holes in 775 T6 before requiring replacement. Aircraft production lines couldn't tolerate that kind of tool changeover delay. Hertzberg assembled a working group with representatives from Douglas Aircraft, Lockheed, North American, and Vultee, the four primary military aircraft manufacturers. The solution wasn't metallurgical, it was operational. Machine speed would be reduced from 2,500 RPM to 800 RPM for drilling operations. Tool life extended from 12 holes to 67 holes. The engineering trade-off was acceptable. Slower machining, but dramatically reduced tool costs and production downtime. By April 10, 1943, Alcoa had produced 2,400 pounds of 7275 T6 aluminum, ready for component testing. The material was distributed to 3 aircraft manufacturers simultaneously: Douglas Aircraft in Long Beach, California, Lockheed in Burbank, California, and North American Aviation in Inglewood, California. Each received sections of the alloy with specifications for fabricating vertical stabilizers, wing stringers, and fuselage frames, the high-stress components that were failing catastrophically. The first production-scale wing assembly using 7275 T6 was completed at Douglas on May 2, 1943. It was subjected to static testing at 120% of the maximum design load. The wing sustained the load. At 150% of design load, the wing remained intact. At 180% of design load, the wing failed, but not through the propagating crack failure typical of 24S. Instead, it showed plastic deformation. The material bent rather than fractured. That's the signature of sufficient strength. The material reaches its limit by physical distortion rather than sudden, brittle failure. The data was submitted to Wright Field on May 15, 1943. The recommendation was unanimous. Authorize full-scale implementation across all military aircraft production lines. On May 23, 1943, the U.S. War Department issued Joint Army-Navy Specification ANW-81, officially standardizing 7075 T6 aluminum for primary structure aircraft components across all military programs. The transition from laboratory to combat readiness had taken 4 months. The metallurgists had delivered. The first F-6F Hellcat with 7075 T6 aluminum primary structure rolled out of Grumman's Bethpage, Long Island facility on June 8, 1943. The aircraft was designated XF-6F3, and it looked identical to the previous Hellcat variant. Visually, it was. Materially, it was a different machine. The fuselage frames, wing stringers, and vertical stabilizer were fabricated from the new alloy. The wing box, the primary load-bearing structure that had consistently failed under combat stress, was entirely redesigned with 7075 T6 components. On June 22, 1943, the aircraft was transferred to Naval Air Station Patuxent River, Maryland for fatigue testing. The protocol was systematic. Mount the airframe on a rig, attach hydraulic actuators to the wings, and cycle the structure through 10,000 simulated combat maneuvers. Each cycle replicated the stress profile of a real dive-bombing run, followed by a high G pullout. The load envelope extended from 0 to 8 Gs, beyond the previous operational limit of 6 Gs that pilots had been restricted to. By July 8th, the test was complete. The 7075 T6 fuselage had sustained 10,000 cycles at 8 Gs without visible crack initiation. Under ultrasonic inspection, a new technique using sound waves to detect internal fractures, the structure showed 0 internal flaws. The alloy had absorbed stress that would have produced catastrophic failures in previous variants within 2,000 to 3,000 cycles. The next phase was flight testing. On July 19, 1943, test pilot Robert Hall took the XF-6F3 to 28,000 feet above the Atlantic. The test sequence was precise: level flight, dive to 420 miles per hour, 8G pullout, recovery to level flight, repeat 12 times. The G-meter recorded peaks reaching 8.3 Gs during pullouts. Hall reported no adverse control response, no vibration, no structural feedback. The aircraft behaved as designed, better than previous variants, in fact. The handling characteristics were crisper because the structure wasn't flexing under load the way 24S aluminum structures flexed. On July 24th, a second aircraft, designated F-6F-301, was delivered to the U.S. Marine Corps Squadron, VF-219, stationed at Espiritu Santo in the New Hebrides, a staging base for Pacific operations. VF-213 was commanded by Major Robert Gaylor, an ace with 5 confirmed kills. His pilots were operationally exhausted. They'd been flying the previous generation Wildcats since 1942, and they'd been losing aircraft to structural failure on approximately 8% of combat sorties. The Hellcat was an improvement but not a solution. The F6F3E01 arrived on July 28th. Gaylor assigned it to First Lieutenant Robert E. Murray, a 24-year-old pilot with 287 flight hours and 3 confirmed kills. Murray's mission profile was combat patrol, 8 hours, 2 combat engagements, maximum altitude 32,000 feet, expected G loading in the 6 to 8 G range. On July 30th, 1943, at 06:15 hours, Murray launched from Espiritu Santo. The engagement occurred at 0847 hours near Kolombangara Island. Murray's flight of 4 Hellcats intercepted a Japanese reconnaissance twin-engine aircraft, a Nakajima C-6N-1 Sayun, a fast reconnaissance plane with a maximum speed of 375 miles per hour at altitude. Standard doctrine called for a diving attack to close the speed gap. The Sayun dove to 28,000 feet. Murray followed, pushing the throttle to maximum, entering a dive at 480 miles per hour, 60 miles per hour faster than previous Hellcats had safely achieved. The stress during pullout reached 8.7 Gs. The 7275 T6 structure absorbed the load. Murray recovered at 12,000 feet and closed to firing range. The Sayun's pilot attempted a maximum load turn, a defensive maneuver designed to force an attacking fighter to exceed its structural limits during pursuit. Murray matched the turn, pushing 8.2 Gs sustained for 4 seconds. The previous generation Hellcat would have begun showing crack propagation under those conditions. This aircraft absorbed it. Murray fired. The Sayun's right engine caught fire. The Japanese pilot dove toward cloud cover at 480 miles per hour. Murray pursued in a sustained high-speed dive, reaching 520 miles per hour, pulling up with a 9.1 G maneuver to maintain firing position. The aircraft didn't break. The structure didn't fail. The fuselage didn't tear. At 14,000 feet, the Sayun was smoking. Murray fired again. The aircraft exploded. Murray recovered and returned to Espiritu Santo with ammunition exhausted and fuel reserves at 12% capacity. The aircraft landed intact. Ground inspection found minor battle damage on the fuselage, anti-aircraft shell fragments from defensive fire, but 0 structural damage from the extreme G loading. The intelligence value was immediate. By August 5, 1943, combat data from Murray's engagement had been transmitted through naval intelligence channels to Wright Field. The report was unambiguous. The F6F3 with 7075 T6 primary structure had sustained G loading 35% higher than previous variants without structural failure. Range was extended by approximately 8%. Climb rate improved by 12% due to reduced aerodynamic flex during climbing maneuvers. By August 12th, Grumman had received modification kits authorizing the retrofit of all F6F3 Hellcats in the Pacific Theater with 7075 T6 reinforcement components. Lockheed initiated immediate conversion of P-38 Lightning fighter bombers. North American released upgrade specifications for the P-51 Mustang series. Republic incorporated 7075 T6 into the next production batch of P-47 Thunderbolts. Within 6 weeks, 156 aircraft had been retrofitted or newly produced with 7075 T6 primary structure components. Combat loss rates among these aircraft dropped from 8.2% per sortie to 1.4% per sortie, a reduction of 83%. By October 1943, structural failure had stopped being a casualty factor in the Pacific Air War. The numbers told the operational story. In the first 3 months of 7275 T6 implementation, approximately 340 pilot lives were preserved by aircraft that would have disintegrated under previous design specifications. The material cost per aircraft was reduced by 14% because less reinforcement was needed when the base material was stronger. Production speed increased by 8% because tool wear reduced downtime. The impossible metal had become standard issue. By December 1943, 6 months after 7075 T6 standardization, the strategic calculus in the Pacific Air War had fundamentally shifted. American aircraft attrition rates had declined by 40% across all combat zones, despite increased operational tempo and more aggressive combat tactics. Pilots were no longer operating under artificial G-load restrictions. The F-6F Hellcat, equipped with 7075 T6 structure, could match the maneuverability of the Japanese Zero fighter in ways previous American designs could not. The Japanese Zero remained faster in level flight and more maneuverable at low speeds, but the Hellcat could sustain higher G-turns longer without structural compromise. The numbers crystallized the advantage. Between July 1943 and August 1945, F-6F Hellcats achieved a 15-to-1 kill ratio against Japanese fighters, a combat efficiency that wasn't driven by superior pilot training or tactics alone, but by the ability to execute maneuvers that would have torn previous aircraft apart. By the end of the Pacific War, American naval aviation had lost 1,147 fighters to enemy action in the Pacific theater. Under pre-7075 T6 operational standards, structural failures would have added an estimated 3,200 additional losses. The alloy directly preserved approximately 2,400 pilot lives during active combat operations. Alcoa's production capacity expanded accordingly. By mid-1944, the facility in New Kensington was producing 18,000 pounds of 7075 T6 per month. Secondary production lines were established at Alcoa's Warwick, Indiana facility and contracted to Reynolds Metals in Sheffield, Alabama. By 1945, total production capacity reached 47,000 pounds per month, sufficient to supply not just fighter aircraft, but also the new B-29 Superfortress long-range bomber program, where wing and fuselage stress concentrations required the superior strength characteristics of 7075 T6. The B-29 program was itself a critical application. The aircraft operated at altitudes above 30,000 feet, at sustained speeds of 350 miles per hour in formation, with fuel loads that created structural stress profiles impossible to accommodate with 24S aluminum. The first production B-29 airframes began incorporating 7075 T6 components in March 1944. The bomber program faced its own production catastrophes. The engines were unreliable, the turret systems malfunctioned, the pressurization systems failed, but the airframe itself remained structurally sound. The material contributed directly to the 50 mission combat requirement established for B-29 crews. Without 7075 T6, that requirement would have been 25 missions maximum before structural reserve was exhausted. Between August 1944 and August 1945, B-29s delivered 169,000 tons of ordnance against Japanese industrial targets, culminating in the atomic bomb missions to Hiroshima and Nagasaki. The aircraft that delivered the first atomic bomb, Enola Gay, piloted by Colonel Paul Tibbets, contained 7075 T6 structural components throughout its primary load-bearing structure. The metallurgical chain connected directly: material science innovation, aircraft structural capability, strategic bombing campaign, war conclusion. Post-war, 7075 T6 didn't vanish into history as a wartime expedient. It became permanent infrastructure for aviation design. The U.S. Air Force standardized 7075 T6 across all fighter designs throughout the 1950s and 1960s. The F-86 Sabre, which achieved a 10-to-1 kill ratio in the Korean War, relied entirely on 7075 T6 primary structure. The F-100 Super Sabre, the F-104 Starfighter, the F-4 Phantom, each successive generation of American fighter incorporated 7075 T6 as baseline material. The alloy enabled increasingly aggressive designs, higher maximum speeds, higher operational G ratings, longer range without weight penalty. In the commercial sector, 7075 T6 became the standard for structural components in civilian airliners beginning in the late 1950s. Boeing's 707 and subsequent commercial aircraft used 7075 T6 in wing box construction, landing gear, and fuselage reinforcement. The alloy enabled the age of routine commercial air travel by providing the structural margin necessary to achieve high-altitude, high-speed operation with acceptable safety margins. The materials science principle embedded in 7075 T6, precipitation hardening through controlled heat treatment, transcended aluminum. The methodology became a template for steel, titanium, and composite material development. The systematic approach to alloy design that Hertzberg and Alcoa had pioneered, varying composition, testing stress response, refining heat treatment, validating at scale, became the operational standard for metallurgical engineering across the aerospace industry for the subsequent 80 years. Alcoa's New Kensington Research Center, transformed by wartime necessity into an innovation engine, continued operating through the remainder of the 20th century. The facility that had solved the structural failure crisis in 6 months became a center of material science research that produced successive generations of aluminum-lithium alloys, engineered composites, and advanced casting methodologies. The organizational capability built under wartime pressure persisted into peacetime as institutional capacity. Modern aviation cannot be understood without 775 T6. Every large commercial airliner flying today, the Boeing 777, the Airbus A380, the Airbus A350, incorporates 7075 T6 in structural components. Military fighters from every advanced air force use variants of this alloy. The material specifications, tested and validated during wartime combat, remain fundamentally unchanged 82 years after their initial implementation. Tensile strength targets, heat treatment protocols, and machinability tolerances are near identical to 1943 specifications. The strategic conclusion is unambiguous. A material science crisis in 1943 wasn't solved by design innovation or engineering workarounds. It was solved by systematically understanding the atomic and crystalline structure of aluminum, recognizing the thermodynamic principles that could enhance that structure, and implementing those principles at industrial scale under impossible time constraints. When operational capability was constrained by material limitation, the material changed. The aircraft didn't need to be redesigned. The metal was engineered to the requirement. The alloy revealed a fundamental principle of warfare and technological advancement. Structural integrity isn't ancillary to capability. It's determinative. An aircraft is not faster, more maneuverable, or more lethal because of its engine power or firepower. It's only effective if the structure survives the stresses imposed by flight and combat. The pilots who flew 7075 T6 Hellcats survived because engineers understood that requirement. The pilots who flew previous variants didn't, not because they were less skilled, but because the material beneath them failed under the same conditions. That principle remains operative in every field where performance exceeds material limits. Aerospace, automotive, marine, structural engineering, medical devices. The answer is never to accept the limitation. The answer is to engineer the material.